Okay guys, unfortunately I didn't have the computer here to actually record the last video on like the previous presentations. So I'm going to be doing this one on paper. My apologies in advance if it's a little bit unorthodox, untraditional, something you're not used to. And this is video number 5. We're going to work on identities and equations. It should also be a short video. So let's go and get started. For this one, solve trig equations. You're going to want to solve trig equations. They're going to require you to pay attention to restricted interval. Example, sine theta equals root 2 over 2 is going to be indicative of why we will actually need to restrict the interval. So let's think, on the unit circle, where is sine theta equal to root 2 over 2? Well, we know, you may recall that root 2 over 2 for sine is true at pi over 4. You may also recall that this is true for 3 pi over 4. That's where the coordinates are positive for your y value, which is what sine is. You get positive root 2 over 2 at pi over 4 and 3 pi over 4. If you're trying to go to 5 pi over 4 though, or 7 pi over 4, those are going to be negative values, so we don't want any of those. Now, each time, that's only on the first and second quadrants, but what if I went all the way around again though? So if I went all the way around again, I would have 2 pi plus pi over 4, or 9 pi over 4 would also be a possible angle. And if I did 3 pi over 4 and I did a full 2 pi, well, 3 pi over 4 plus 2 pi, that's going to be 11 pi over 4. So now I have 4 angles that have the same answer, root 2 over 2. Now, if you're catching on to this, we could revolve around 3, 4, 5 times, however many we would like. So here's what our answer is going to be. Our theta is going to be equal to pi over 4 plus 2 pi times k. K is going to belong to integers. And what this fancy notation means, and I did this backwards, what this fancy notation means is if I have k be 0, 2 pi times 0 will be 0, so I'll get a pi over 4. If I have k times 1, it will be 2 pi plus pi over 4. If I have k times 2, the k is standing for the number of revolutions and whether you want it clockwise or counterclockwise. This equation will allow me to generate an infinite amount of solutions, which is what our trigonometric equation yields. Here's your other answer, 3 pi over 4 plus 2 pi k, 2 pi times k, and again, k is going to belong to integers. That can become somewhat tedious if we have a lot of equations to solve, which is why you may see a problem like this, where you have an interval restriction from 0 to 2 pi. 0 to 2 pi is just going to be the first through the fourth quadrants in one revolution. So here, our answer is going to be much easier. It will be pi over 4 and 3 pi over 4 only. We don't need to revolve around again because my limit is only one revolution from 0 to 2 pi. And it's saying, look for any angle that yields root 2 over 2 in that revolution. And that's what pi over 4 and 3 pi over 4 signify. Okay, next one. And I'm sorry that this automatically zooms in and out. Again, my apologies for not having this on the computer as I did in the previous videos. 2 sine squared x plus 3 sine x plus 1 equals 0. I don't think you'll have a problem like this in calculus, but the only reason I'm having you do this kind of problem is so that way we can practice with this interval notation because that is a part of calculus. So let's go ahead and try this without a calculator. It looks like it's a quadratic. So 2 sine x and a sine x here. It's a positive 1 and a positive 1. I'll check 2 sine squared x plus 2 sine x plus sine x gives you plus 3 sine x, and then the positive 1, this checks out. Now I'm going to get sine of x is equal to negative 1/2. and I'll get sine x is equal to -1. Okay, let's solve. So for sine x equals -1/2, I gotta think on the unit circle, only between the first to the fourth quadrants in one revolution. And where is sine x equal to -1/2? That happens at right here, which is 7 pi over 6, and right here, which is 11 pi over 6. I also need to think, where does sine x equal -1? Again, on a full revolution, -1 happens right here. The sine is -1 at 3 pi over 2. These are my answers. 2 sine x plus 4 equals 2.75. Let's go ahead and do this. We'll go and subtract the 4 over. Sine x is equal to -1.25. And then when we cut that in half, we have sine x is equal to -0.625. Now here we're going to get a negative angle because this negative radian is going to be the fourth quadrant. So I'm going to need to do x is equal to sine inverse of -0.625, which is about, let's find out what that is. So let's do 0.625 negative. Let's do a negative. Let's do a sine inverse. Let's get this in radians, and let's try that again. So 0.625 negative sine inverse. Okay, that's about equal to negative 0.675. Please keep in mind, though, that again, that radian measure is going to be right here in the fourth quadrant going backwards. We need from 0 to 2 pi. So my answer, x is going to be equal to 2 pi minus 0.675. And I'm going to have a similar y value in the third quadrant, so I'll have pi plus that value as well. And you are welcome to get the decimal answers. I'm going to go ahead and move on. This page is just a whole page of identities. Let me get this out of your window for you. This page is just a whole bunch of identities. I would strongly recommend to review this on your own, study these. We're going to use them in the next examples. So, verification of identities. Let's go ahead and give it a shot. First one, tan theta over secant theta equals sine theta. Let's see if that's true. Tan theta divided by, I'm going to write the division like this, secant theta. Now, secant theta is equal to 1 over cosine theta. And we still have division. And tangent theta is equal to sine theta over cosine theta. And my whole job here, if you don't remember trigonometric identities, is to get one side to look like the other. It's not an equation. We're trying to get the left side to look like the right side, or sometimes the right to be like the left. Now, I notice here that my cosine thetas are going to cancel, and I am indeed left with sine theta is equal to sine theta. That's good to go. Sine 2 theta equals 2 sine theta cosine theta. Okay, this one I'm going to use this I'm going to use this identity. And if you're looking on that sheet previously, this is going to be the sum addition formula, or the sum formula. Sum addition would be redundant. So I am going to be using this sum formula right here. Sine 2 theta happens to be sine of theta plus theta. And since I have angle addition, I am going to be able to use this formula here. So that means I'm going to have sine theta. Notice that since A and B are the same thetas, I can just do sine theta cosine theta plus sine theta cosine theta. Well, it looks like I have two of those, so now I have 2 sine theta cosine theta, and that does indeed equal what we have on the left, I'm sorry, on the right side of the identity, 2 sine theta cosine theta. Finally, prove sine squared theta equals 1 minus cosine 2 theta over 2. Notice this is a proof. This is not a verification for an identity. So here's what I'm going to use. I know that cosine squared theta minus sine squared theta is equal to cosine 2 theta. That is a double angle formula. And the double angle formula is going to be right here. I know that cosine 2 theta is equal to cosine squared theta minus sine squared theta. Now, I also know the Pythagorean identity, and I hope you'll know it as well, that cosine squared theta plus sine squared theta equals 1. I'm trying to prove that sine squared theta is equal to 1 minus cosine 2 theta over 2. I'm trying to prove the power reduction formula. Well, I have this cosine squared theta, which I don't really want. And I noticed that cosine squared theta, if I move the sine squared theta over, is 1 minus sine squared theta. Thus, I can replace my cosine squared theta here with 1 minus sine squared theta, and then bring down everything else, minus sine squared theta. Nothing's changing on the right side of the equation. Next, I'm going to move this cosine 2 theta over. So I have 1 minus cosine 2 theta over 2. I'm sorry, 1 minus cosine 2 theta. I notice that these two sine squared thetas are both negative on the left side of the equation. I'll move them to the right side of the equation though. And if I divide everything by 2 on both sides of the equation, I do indeed get that sine squared theta is equal to 1 minus cosine 2 theta over 2. And this is my proof of the doubling of the power reduction formula. I told you guys that that would be a short video. I hope it was. And thanks for watching.